All right, so let's figure out our probability here. We have a survey of college students that finds that the probability they like country music is 0.4, probability they like jazz is 0.3, and the probability they like both is 0.1. What's the probability they like country or jazz? So when we see or is what operation? Addition. All right, so our probability here, so the probability they like country or jazz. Right, so or is, this is union here means or. It's going to be equal to the probability they like country plus the probability they like jazz. Oops. Trying to color code it. Probability they like jazz. And then we're going to subtract out the probability that they liked both, because we counted these people twice. We counted them once for country, and we counted them once for jazz. So that symbol there means and, because if you liked both, you were counted in both the country category and the jazz category. All right, so let's see if we can figure out, we can put all the values in here and do the probability, and then let's look at a Venn diagram that goes with it. Anyone at the orange table? So what's the probability for country? They're just 0.4. When the probabilities are given as a percent or a decimal, you're already given it in a reduced form. So you don't have to figure out total. All right, so 0.4. How about the probability they liked jazz? Blue 4. And then we're going to subtract the probability they liked both. Yellow 5. So our probability here is going to be 0.4 plus 0.3 will be 0.7 minus 0.1 is going to be 0.6. Oh, this is in your notes, remember, on the third page. Let's just draw a Venn diagram to see what this looks like, because this will help us later on when we're looking at Venn diagrams. All right, so we have the country. I'll put C for country. I'll put J for jazz. All right? All right, and then we have our intersection. Let's work, whenever we're doing a Venn diagram, you want to work inside out. Right? So for a Venn diagram, work inside out. It's easier to figure out the inside. So inside means that intersection. Right. So how much is in the intersection here? How much do we have in the intersection? No? Yes. 0.1 here is in the intersection, right? That's the probability they liked both, was 0.1. Now, how much is the probability, what should go in the just country? Not 0.4. No. No. You at home, see if you could figure it out before they figure it out. Was it? You are correct. Ding, 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 ding. That is correct. 0.3 is correct. Now, can you figure out what's in the jazz? Not point, what'd you say? 0.2. Because this is together is 0.4. These are the people we counted twice. Is these people right here. And then this together is 0.3. So notice together, this is 0.4. And then together, this is 0.3. Now, how many people go out in the outside section? In other words, how many don't like either kind? What was it? 0.4. Because together it has to add up to 4 plus 0.3 plus 0.1 plus 0.2 is going to give us 7, 8, 9, 10. That adds up to 1. That's everybody. That's 100%. Probability of 1 is 100%. Add all of this to your notes. So you see how we worked on so this goes on the 3rd page. Add all this to your notes. If you run out of space, so you can have a sticky note or, another piece of paper, but I have a sticky notes if you want a sticky note. So now, anyone who's watching this podcast, including those who were in the podcast, the very first podcast on the lesson, I didn't go over this with first period, so it's going to be this particular problem. So I'll give you we'll give you directions that you can skip watching this problem again, unless you didn't understand how I did it. Then you can watch it again. So if you're watching this podcast and want to see it again, you can see it again. Watch me do it on the podcast, on the Nearpod. Everybody good? Good job, Corey, figuring that out. All right, so we won't do, maybe we'll do one Venn diagram for the very first one, just to give you the kind of the hang of it with the cards, and that's it, because there's a lot of elements in our, and we kind of have to do like a little kind of, not a complete Venn diagram, because I don't want to list everything. All right, so we want the probability of drawing a king or a heart. All right, so we'll do a little Venn diagram for this one. All right, so this is the king category, and this is the heart category. All right, and then we have, of course, the elements that don't fit into either of those. All right, so who should go? So let's go through all the different cards and see where they should go. How about the king of clubs? Where should the king of clubs go? And king. All right, so here's, and you gotta look at my drawing. Here's king, and I can't really draw any of these things. Wait, clubs is this thing. So there we go. King of broccoli. Someone said earlier. King of broccoli. How about the king of spades? King. In the king category. Okay, let's look at the spades. Yeah. Here, use your imagination. King of leaf. Especially with these pens, I really can't draw. How about the king of hearts? In the middle. A heart looks like a heart. And then how about the king of diamonds? King. What should go over in the hearts category? Squares. What's that? King of squares. King of squares. What should go in the heart category? What's that? We got king of hearts. He's in the intersection. We have ace of hearts and two of hearts and 4, 5, 6, 7, 8, 9, 10. Yeah.
Just put hearts.
That's king. 7. These hearts are getting worse and worse as we go along. 8, 9, 10. Oh, we got to squeeze them in here. Here's jack, and here's queen. All right, everybody squeezed in there. And then, where should I put all the other cards? Outside. All right, so these are other cards. Yeah, all the other cards, right? All the jokers. Yeah. So those are things like the diamonds, other than the king of diamonds, etc. All right, so all the other cards can go out there. I'm not drawing those off. So let's figure out our probability here. And I just did that to just kind of help us with the first one, because sometimes people aren't familiar with how many cards are in, what cards are in the different suits and how many there are and so forth. That's what's the orange king. That's the only Venn diagram we're doing with the cards, because there's too many elements. All right, so we want the probability of king or heart, which means we need to find the probability. I can move this up a little bit. I could stand to have a little bit more space to write here. Let's move this up a little bit more, a little bit more, a little bit more, a little bit more. There we go. All right, so probability of king or heart is going to be the probability of the king plus the probability of heart. And then we're going to subtract the probability of king and heart. So the and is going to be the intersection. And means intersection. All right, so how about the probability of getting a king, green 3?
The probability of getting a king is 4 out of 52.
Yep. Yes, 4 out of 52, sorry. 4 out of 52 is our king. We have 4 kings here, right, in the king category, and 52 cards. How about the probability of a heart? Anybody at the red table? 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. So 13 out of 52. And then we have to subtract the overlap, because some things have been counted twice. So we don't want things that to be counted twice. So what's the probability of heart and king? Red 5. Yep. All right, so we have 4 plus 13, which gives us 17. Then minus 1 is going to give us 16 out of 52. Now we need to reduce, so 4 13s, yep. 13 is a common denominator with the cards, because there's 13 in a suit. All right, so this one was in your notes. Go ahead and put this one in there. Any questions on this one? Yeah, you can move that into space.
Olivia borrowed a compass.
Ah.
That was a reminder to you to
Thank
remember
you.
to do that.
Gotcha. I need new compasses too. They're kind of. Let's see if I can order new compasses for next year.
They're not right.
No, they're too swingy. I have the one kind of compass, but it's hard to do constructions with it. You can do circles, but hard to do constructions with it. Everybody got this? Everybody good? Okay. I keep forgetting. All right, so let's do this problem together. A card is drawn from a deck of 52. Find the probability of each. We want to find the probability of drawing a red card, hearts or diamonds, or a face card. All right? We're not going to draw all of these ones out, but maybe we'll list some just to help us remember. All right? So we need the probability of the red card. All right? So what's the probability of getting a red card? Anybody at the green table? Yes. And I'm going to actually write it as 2652 because it will help us. We probably going to have 52 as a denominator. Yeah. So we'll wait to reduce because we'll just have to change it back. But yeah, half the cards are red, half the cards are black. How about the probability of a face card? Now, face cards have faces on them, right? Has to have a face. So what's the probability of a face card? purple 3.
Well,
Yep, so there's 4 of each of these, right? There'd be a heart,
one for each.
a diamond, a broccoli, and
Leaf.
and that looks like a heart again. I think I'm going to teach art classes. I actually could draw better than this, but no, look at that. That's not too bad. Not with this giant thick pen. So we have 4 of those for each of those 3 categories here. And then how about red and face? So let's list our red and face cards, because that'll probably help us remember. So anybody at the purple table, what are the red and face cards? So give me examples of some cards that are red and face.
Queen of hearts.
Queen of hearts.
King of hearts.
King of hearts.
Jack of hearts. On and on for about one
King
more.
of diamonds,
King of diamonds.
queen of diamonds, and jack of diamonds.
Yep. Oop.
Those last 2 aren't diamonds.
Jack of Jack of quadrilaterals. Woo!
Baseball and baseball.
It's the Jack of quadrilaterals.
It's like
Anyway, what's a diamond anyway? It's not a diamond, it's a rhombus on the card, or sort of.
Queen
All right, so there we have. So what's our probability going to be for red and face? No orange 1. Do we have an orange 1? No. Red 2. What's the probability for red and face? Yeah, 6 out of 52. So our probability is going to be 12 plus 12, 26 plus 12, which will give us 38. Minus 6, that's going to be 32 over 52. What would that reduce to? Eight thirteenths is correct. Both of those are divisible by 4. You got to kind of figure 4 with the 52. Doesn't have too many factors. It's 4 and 13. Yeah. Any questions on this one? All right, let's do another one. All right, so this one is in your notes a little further down. And we have, they're even doing Venn diagrams, but this is not a problem that lends itself to a Venn diagram. So if you have 2 different groups, or 2 or more, I should say, not even just 2, 2 or more different groups, because I could have 3, 2 or more different groups, evaluated on 2 or more characteristics use a table, not a Venn diagram. I just put Venn diagram. Right? Because Venn diagram lets us evaluate a single characteristic, right? A single grouping, right? So we can have 2 groups, we can have 3 groups, but we're looking at, do you go in this group, do you go in this group, do you go in this group? If we've got, are you in this group? And if you're in this group, are you this one or are you that one? So that's too many groups, right? So when we have that, when we have to compare on different characteristics, we're going to make a table. A table will be easier. Right, so let's make a table. And we have 2 characteristics here. We have the class you're in, we have juniors and we have seniors, and we have read a paper, don't read a paper. If you've got 2 characteristics, if you've got 2 and 2, you're not going to have 2 columns and 2 rows and 2 columns. You're actually going to have 3 rows and 3 columns. So the number of rows and columns is 1 more than the characteristic. So if there's 2 groups, junior, senior, you need 1 extra for the total. All right, so we're going to make 3 lines here. 1, or 3 boxes. And then we're going to make 3 boxes again. Because we need one for the total. All right, so this should give us, did I put in enough spaces here? Oh no, I'm still short. Because I got to write juniors and seniors. I need one more, don't I? Yeah, I do. Ooh, sorry. Add one more for that. So if you find out you don't have enough rows for your column, because I got to write that, I forgot, I got to write the categories. So I need 9 boxes just for the numbers. I need more boxes for the categories. So make that 16 instead. So if you're ever short rows on your table, just add some more boxes to the sides, and then you'll have enough. And if you have too many, well, you can always erase it. All right, so we have to evaluate them on whether they are a junior. Let me write that word better. Seriously, get out of the box. Actually, what I should have done is I have a thing up there I can make a table with. The only thing is sometimes my words get stuck in there. So we have junior and we have senior. And we also need to know the totals. Right? Because when we figure out probability, it's favorable over total. We need a place to write down the totals. Right? And then we have paper. So we have read paper, no paper. No read paper. Oops. No read paper. And then again, we need a place for total. So when I said 9 by 9, I really meant 3 by 3. I really meant 4 by 4 because I forgot I need a column to write the labels in. So you have one for the labels. And this box, well, that's an empty box. I have nothing there. The one that's in the upper left-hand corner there. And then I need to have totals all the way through. Because I need to know how many juniors, how many seniors, and how many total read the paper, how many total don't read the paper, and how many total people. So let's write down what each of these means. So this total here means, and add this to your notes, it means total juniors. That's the total that one is. This column here means total seniors. This box here means total altogether. So when we add across here, total juniors and total seniors needs to add to the total people. Going this way, we have total read paper, total no read paper, total no paper. Right? And when we add these totals across, it needs to add up to the total number of people. Right? Yeah. So both ways, our totals need to add up to the total number of people. Let's put the things in the boxes where they should go. All right? So I'm going to have you help me and tell me where any number should go. Oh, let's read the question first, and then tell me where any number should go. Of 1,560 students surveyed, 840 were seniors, and 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were juniors. What's the probability that a student was a senior or read a daily paper? If you try to do this probability question without your table here, you're likely to make a mistake. I would probably say 90% of the time you're probably going to have the wrong answer. But if you set up your table, you will have the right values in your table. And it only takes a minute, right? I mean, it hasn't taken us that long, and I spent most of this time talking. So green 5, tell me where any number in the table should go. Any number, where should I put that in the table? I need to put the numbers in the table. Tell me where any number goes.
215. Red paper, juniors.
Red paper for juniors. So this is where 215 goes. Right? Because 215 of the juniors read a paper. All right, purple 4. Tell me where another number should go.
1,560
is the total. Total. That's how many students we have. Yep, the total of the totals is right there. All right, so we got a couple more numbers in the table, and then we're going to have to use what we have to figure out the rest. Red 1, tell me where another number should go.
The 840 on the total seniors.
840 total seniors. And then there is one more number we need to put in the table from the question itself. Anyone at the yellow table, where's the last number from the question go?
So we 630.
Where should I put that?
Seniors read paper.
They're not the seniors that read a paper.
We're 840 seniors.
They're just 840 seniors, 630 read a paper. Yeah, total paper. Yeah, so this 630 doesn't have anything to do with the seniors reading the paper. All right, so now those are all the numbers we were given. We have to use what we were given to get the rest of the numbers. All right, so tell me another number from the table. Blue 3. Can we use what we're given? Because we know that we have to, our totals have to add, we have to add to the total. Well, yeah, our totals have to add up. Do you want me to come back to you? Call on someone else? I'll come back to you. All right?
415 for seniors for red paper.
You are correct. All right, so does everyone see how, let me write that nicer, that 215 and 415, when we add those together, those equal 630. All right, want to try again? Try again? $720, yep, for the total juniors. So we have 700 total the juniors. Green 4, want to do it? Yep, 30 for total red paper. Orange 4. Do we have an orange 4? No. Orange 2. We got 2 columns left, two spots left.
For the
505. What's the last one? Anyone at the blue table? 425. The numbers all make sense, everyone? So you might have, this might be your closing, and you might have a question on the whiteboard practice on Monday, is to be able to make the table and then find the probability. So now once we have the probability, we can set that up. We want to find the probability that a student was a senior or read the paper. So we have probability senior or paper is going to be equal to the probability for the senior plus the probability for the read the paper, and then plus the probability, excuse me, not plus, minus. We have to subtract off the overlap. So get rid of that. Plus, that should be a minus. So we're subtracting the intersection area for the probability for senior and paper. So these are people that fit into both categories because we've counted them twice. We counted them once for seniors and once for paper. And then I'm going to move this down here because I have more space, except for the one random 2. And then perhaps I can move this up and we can put the answer to our question underneath. And then we will be done with this question. And actually maybe we'll do another question about this problem. All right, so what's the probability for senior? Orange 3. No, orange 3. Going back the other way. Do we have an orange 1?
Yes.
So orange 1, what's the probability of senior? Over? Yep. 15, 16. 16. All right, and so then we got that probability for senior. And then how about the probability of red the paper? Green 4.
630.
Yep. Now, some people were counting more than once because they're in each category. So we have to subtract those people off. So what are we going to subtract off? Orange 4? No. Orange 2.
Subtract 415.
Yes. So we're going to subtract off 415 over 1560. So we'll add those up. We've got 840 plus 630 is going to give us 1470. All right, so 1470 minus 415 is going to be 1055. And then 1560. If it's divisible by 5, so this would be 211 and 312, right? And I didn't see that this tape was 31 minutes, so I'm going to stop it and then pick up again. Bye for now.